Thank you for joining in again. In the last two videos this week, we will state, discuss, and prove the Rees representation theorem. This is the first very big theorem that will be discussed in this module. Now, before we get to that, so while I was editing the last video, I realized that early on in the video I misspoke at one point, and precisely at the following point. We started by saying that if you have a Hilbert space and a closed subspace, and then that's gonna be again a Hilbert space, and that's a correct statement, there's nothing wrong there. And when I explained why that is the case, I said, okay, you start with the inner product in the big space, you restrict the inner product, everything was fine there. And then I said, now you have a closed subset, and that itself is complete, right? And for this you need a theorem or a result from the metric space module, and there at one point I misspoke. So in the metric space module, what one proves is if you have a complete metric space, then any subset of it is also complete if and only if it is closed. While I was recording the video the other day, I said if and only if any subspace is closed, but that doesn't make any sense because the subspace is only defined in vector spaces, and in general a metric space is not a vector space, right? So that was the one point. I said subspace, but what I should have said is subset, okay? But the result was still all okay, and then in particular the application of the result in the theorem about the best approximation was everything was good, okay? Good. Now let's get started here. So after we did the best approximation result last time, so this has to do with given an arbitrary vector in a Hilbert space, you can sort of best approximate it by a closed convex subset, or then as a special case, as a corollary, you can do it with closed subspaces. Now we're going to use this to prove the first sort of building block that will be used crucially in the proof of the Rees representation theorem, and this is displayed here on the slide. So this is a projection lemma, although it's really a theorem. Some people call it a decomposition theorem, but we will reserve that terminology, decomposition, for something else later in the class. Okay, so this will be just the projection lemma. Okay, what it is about? Well, actually something that you probably know from linear algebra. So let's first read it. So H a Hilbert space, S a closed subspace. Then you can, well, that's why it's sometimes called decomposition theorem, because you can decompose a given X into, well, two parts, a part Y and a part Z, where Y comes from the closed subspace and Z is in the orthogonal complement. Remember the orthogonal complement we defined last time is the set of all vectors that are orthogonal to everything in S. Okay. Symbolically, you can write it in this fashion here. So this is on the left, this is a sum of two subspaces. So this here, this equality simply means that any X in H you can write as something in Y plus something Y in S plus something Z in the, well, orthogonal complement. And this decomposition is unique, right? So here the important word is you can uniquely write it as such, and this means in particular that the intersection of these two subspaces, which is again a subspace, it's a general fact in linear algebra, has to be the zero vector space. So the vector space consisting of the zero vector. Okay. Now, why is this maybe known from linear algebra? Well, at least again in R2 I can draw a nice picture and visualize it. So remember, in R2 the only non-trivial subspaces are straight lines through the origin that I've already said several times. And now what's the orthogonal complement to that? Well, it's again straight line through the origin. That's the one here with the 90-degree angle. And what this theorem really says is that these two lines, the green one and the pink one, they span the entire plane, which you can clearly see. You can write any vector in R2 as a linear combination sort of this basis vector and of this basis vector. This is really what's written here on the left, and as you can see in the picture, these subspaces, they only intersect in the zero, right? That's the only intersection point here at the origin. Okay. Good. Again, I've said this multiple times. the geometrical visualization here is nice, but it doesn't really help you to prove this in infinite dimensions. But I thought I mention it anyways. Okay, so how to prove it? This is actually now fairly simple, since we have the best approximation, because we will use it. So given, there will be two parts to this proof. First, we will see that we can write any x as y plus z, and then we will argue why this is unique. Okay, so given x in H, let y in S be the best approximation. Be the best approximation of x by vectors in S. This was the last theorem which guaranteed that such a thing uniquely exists. Okay, now set difference vector z as x minus y, and then the corollary to the last theorem showed that this is a vector in the orthogonal complement of S. Okay, set this, clearly I can write x as y plus x minus y. Okay, here's your z. And obviously the first one, y, is in S. That's the best approximation. The second one, z, by the corollary, is in the orthogonal complement. Okay, so immediately within one line you have the existence of such a decomposition because you have the best approximation. Okay, any vector here in my Hilbert space, given a closed subspace S, I can write as something in that closed subspace plus something else in the orthogonal complement of the closed subspace. Okay, that's part one. Now uniqueness. For uniqueness, suppose that the x can be decomposed, say, as y1 plus z1, and then also as y2 plus z2, where the yj's are in S and the zj's are in the orthogonal complement. Okay, then let's do some algebra. So I'm going to look at this. Well, it's a double equality, but I'm just going to look at the middle piece. So I'm going to take the y's to one side and the z's to the other side, like this. Now remember, both S as well as its orthogonal complement are subspaces. That means they are closed under taking linear combinations of elements in them. So this means in turn the left-hand side is in S, because the yj's are in S, and S is a subspace. And it also means that the right is in the orthogonal complement, because the zj's are in the orthogonal complement, and the orthogonal complement is a subspace. Right, so this means actually, because they're equal to each other here in this line, that they are in both S and the orthogonal complement, which is the, well, intersection of these two subspaces. Yeah, but this can only happen if they are the zero vector. Why? So why is this equality true here? Why is the intersection of S and the orthogonal complement a zero vector? Well, you can prove by set inclusion. First of all, the zero vector is contained in both S and the orthogonal complement. So why is that? Because any subspace contains the zero vector. Okay. So, but why is an element that is in the intersection automatically the zero vector? Well, look here. If something is in the orthogonal complement, if x is in S perp, then the inner product xy is 0 for all y in S, right? This is the definition for all y in S. Yeah, but if x is not just in S perp, but also in the S itself, then I can insert here y equals to x, right? Because this inner product vanishes for all y in S, and if x is also in S, then I can replace y is equal to x in there. Yeah, but if you do this, you have that this is equal to 0, and this is of course one of the properties of an inner product, that this is only going to happen if x is equal to 0, right? And so the other set inclusion is also true, and that's why the intersection there of S and the orthogonal complement of it is equal to the zero space. And then it's clear now, right? So then this means these vectors both have to be equal to 0 And that just says that y1 is equal to y2 and z1 is equal to z2. Okay, and that establishes uniqueness. Okay, that's the proof. That's short, provided you have the best approximation. For the best approximation, we had to work a little bit. Okay, this was parallelogram identity, had to be exploited twice. Okay, good. Now let's move on. Let's pull some corollaries out of it, and then we will get to the Riesz representation theorem. Okay, so first corollary: if S is a proper subspace in a Hilbert space H. So what does that mean? Well, S is not all of H, right? So that is S is not equal to H. Okay, then its orthogonal complement will contain more than just a zero vector. Okay, the zero vector is always in there, but if you start with a proper subspace, then the orthogonal complement will contain more than that. Okay, how to do this? Well, that's a consequence of the projection lemma. So if S is a proper subspace of a Hilbert space, then I can find a vector in the Hilbert space which is not in S, right? That's what proper means after all. Yeah, but then in the projection lemma, we must have that z is different from 0, right? So the projection lemma was this: x is equal to y plus z, where this guy is in S and this is in the orthogonal complement, right? So, and this is a unique decomposition, a unique representation of any vector in the Hilbert space. Yeah, but if x is not in S, then automatically this here, that z must be non-zero, right? Because if it were 0, because this is a unique decomposition, then my element x would be in S, contrary to the assumption. Okay. So we have this, so z is different from 0, since I already indicated in yellow, since z is in the orthogonal complement, we have then that the orthogonal complement contains more than just a zero vector. Okay, that's the first corollary. Pretty simple. At least again, if you think about R2 and draw these two subspaces, then it's kind of obvious, because as soon as you take this straight line, the orthogonal complement is that other straight line has more than just a zero vector in it. If you, on the other hand, take S to be the whole R2 plane, then of course the orthogonal complement would be the zero vector. Okay. Another corollary that actually, now this differs sort of from linear algebra in that you really see the influence of possibly infinite dimensions. So let's write it down, and actually you will prove this one in the exercises. For any subspace not necessarily closed, call it T for some reason, of a Hilbert space H, we have, well, so the question is this: you can start with T, okay, and then you can make sense of the orthogonal. You know what, I will call this S, otherwise these T's upside down, they're kind of confusing. So let's call it S. So you start then with S, you form the orthogonal complement. Okay, now we have some understanding of this. And now the orthogonal complement is a subspace, actually a closed subspace. I discussed this. So now you take the orthogonal complement of that thing again. So the question is, what are you gonna get? Let me draw my picture here again. And this is really where the picture now is super deceiving, because if you start with this guy, and then you go to the complement, right? And now if you had started with the red line instead of the green line, so, and then figured out the complement of the red line, then of course you would draw the green line, right? So in finite dimensions, that's true. I mean, here this is just by pictures, but you can easily prove this because you have finite dimensions. The dimensions add up perfectly. Okay, you can easily show that the double orthogonal complement and the original space, there is some easy containment, okay? And then if it were proper, you just compare the dimensions and then you get a contradiction. So they have to be equal to each other. But here in infinite dimensions, you can't count the dimensions. So actually what comes out here, and you will prove it, is not S, but the closure of S. So the set of all limit points of S, right? So there's a really a significant difference between finite and infinite dimensions that you see entering here, okay? At the moment, we will leave this to the exercises. This corollary, we're going to use it later, in particular in chapter 4, okay? It's a useful helper. Okay, now what we will do now is indeed now finally the Riesz representation theorem. So I'll first state it, and then I will say several things about it, and then we will begin its proof and then probably finish the proof in the next video. So Riesz representation. Again, depending on who taught you linear algebra might know this theorem already. At least in my linear algebra course I always mention it. It's easier to prove there because I have basis and all of that. But here the same statement holds. So let's state it. So let H be a Hilbert space and f a continuous linear functional. So remember this notation. You take a non-linear space and you put a star on top. So these are bounded linear transformations from the space into the scalar field. Okay. These are called linear functionals, and we call the space the dual space. Now you can ask yourself, how do those continuous linear functionals in a Hilbert space look like? And the remarkable fact is, which is the content of this theorem, that you can write them down explicitly. So this is really a remarkable statement in that you only have this in a Hilbert space. We will discuss other spaces later on, and there you don't have such straightforward representations anymore. Okay, so let's see what we can do. Then there exists a unique vector y. Well, y of course depends on the f that you start with, such that... Okay, so how could you construct some linear functionals in a Hilbert space? Well, you could take an inner product, right? So here's your y, that's sort of fixed, and x is the variable, okay? And remember, the inner product is linear in the first vector, and it maps a pair of vectors to a scalar, okay? So this certainly here, this guy is a linear functional, okay? It goes from Hilbert space H into the scalar field, all right? Now the beauty here, the remarkable fact of the Riesz representation theorem is that all functionals are of this form for some unique vector small y, okay? And that's it. So this is a theorem that characterizes all linear functionals on an infinite dimensional Hilbert space. It's really remarkable. There's some other parts to it that we will use later on. So let me first write here for all x in H. Okay, the second part is in addition, you have an equality of norms. Okay, so but now here careful. So the norm here on the left, this is the usual norm induced by the inner product. Okay, the norm here on the right, because f is a functional, this is the operator norm, okay, or functional norm. Okay, so this thing is the supremum over non-zero non-zero h of f of x over x. Okay, nevertheless, the theorem says that these two norms are the same. Okay. The Riesz representation theorem is extremely easy to state, and as it turns out, if you have the right preparations in place, which is the projection lemma, that's why we did it up front, it's also really easy to prove. It's a remarkable theorem in that it is so simple, And later on, when we will in chapter 3 discuss dual spaces in much more detail, this theorem will actually help us to identify the dual space of any Hilbert space. Again, this is a feature that for other spaces like Banach spaces that we will discuss in chapter 3, you're not going to have. Okay. Good. So let's get started. So the proof idea is use, well, the projection lemma. And in a sense, construct that, functional explicitly in terms of the inner product. Okay, so set S as the kernel of the linear functional. Okay, and recall, because the projection lemma needs closed subspaces, so the kernel, fortunately, is a closed subspace. Is a closed subspace. Okay. Now, two cases can happen. S is already the whole Hilbert space. Okay, that could happen. Yeah, but then this means that F, my functional, sends every vector to 0. Okay. Then f of x is equal to 0 for all x in H. Yeah, but that 0 you can also get if you take an inner product and put one of the vectors equal to 0. And of course, he will take the second one to 0. So we are finished in this case because up here it says for any given f, I can find unique vector y such that I have this representation. Yeah, but if S is all of the space, then f of x is equal to this one, and here is your choice of y. Okay, and you're done. Okay, so that's easy. Okay, now of course harder. Hence, assume S is a proper closed subspace of H. Now remember, after the projection lemma, we had two corollaries. The first one was if you have a proper closed subspace, then its orthogonal complement contains more than just the 0 vector. And that's what I'm going to use now. So there exists non-zero vector in the orthogonal complement. Let's call it x0. Okay. Now define following quantities. I have to cook up this y up there. Right. So this is done constructively here. Fx0, here complex conjugate bar, x0 and x0, let's see here, a square. Okay, so this is just a multiple. Remember, f is a linear functional. So this guy here out front is a scalar, and you divide by the norm squared. That's also a scalar. So this is that vector y is just a multiple of x0. So, and then hence in particular, because S perp, the orthogonal complement, is a subspace, that guy is in that subspace. Okay. Define this so that f of x is equal to 0 is equal to x, y for all x in S, right? So why is this? Well, this equality here, the first one is because S is the kernel of f, right? So that will be sent to 0. And the second equality is because of the definition of the orthogonal complement, right? Y is a vector in the orthogonal complement. That means it is orthogonal to everything in, well, S. And that's precisely what's written there, okay? So this is true, all right. Further, if x is now any multiple of x0, then let's play around here. F of x is what? So f of alpha x0. Now f is a linear functional, an arbitrary linear functional, so I can pull out that scalar. Okay, but now let's do here some computations. I will write here something. I will write alpha x0. This sort of explains the peculiar form of my y vector up there. I will write this. So, and my claim is this is actually an equality. And why is this? Well, because of the properties of the inner product. So the inner product allows me to pull out the alpha. It allows me to pull out this guy with a bar on top. And the same thing here. Also here, this goes out with a bar on top. Yeah, but then what you have? You have out front alpha fx naught, and then inner product x naught with x naught divided by length squared. Yeah, but that is precisely 1. So indeed you have here equality. Okay. Yeah, but this is by definition of y, alpha x naught y, and since x was alpha x, this is precisely x comma y, as you would like it. So now you have to read that this is equal to that. Okay, good. I think I will stop. Yeah, it's a good point to stop right now. So we will, there's not much left in the proof. We are almost there at the existence, then we will establish the uniqueness, and then we will move on actually to the next section in the Hilbert space chapter. Okay, see you soon.